This video will begin our discussion of section 2.6. This is part 2. This is about Bernoulli equations. So we were going to define what a Bernoulli differential equation looks like, and then we'll solve it. There isn't a whole lot of intuition here on like which way to take, on like why we would multiply by a certain thing or something like that. It's just a method, and we're just going to use this algorithm, this method, just to get through and solve the problem. So yes. So let's begin. The form of a Bernoulli differential equation, and it's completely based on form. Just like linear equations were based on form, it almost looks like a linear equation, except for I get this factor of y over here to some power. The power is not going to be a 0 or 1. It'll be something else. It'll be higher. But we're going to take note of what this n is. And then we're going to run through a whole method. And I'll try to highlight the formulas as we go through. So I'm not going to run through the method right now. I am going to work a problem out to show you an example of how it works. And then you can go back and look at this method for your reference. Try not to rely too much on a method like this. Keep looking back type thing. Try to, when you're starting to work, because now we're starting to get to equations that look very similar. Now you need to start working on bringing up certain problems and start thinking about the method that you would use for that and start memorizing the methods. All right, so this first example, I can't tell what it is looking right at it because it's a bit different than the form above. The form above, if we go back and look, it has dy over dx by itself, dy dx. So I'm going to get that by itself first. So dy dx, I'm just dividing everything by that 4 over that. So I get a 1, I get xy over 4x squared plus 9. And let's go ahead and pull that y out over here, just because it's a y, equals, okay, and I'm dividing by the 4s cancel, and then 1 of the x squared is plus 9, so I get x squared plus 9 times, and then it's y to the negative 3. Make sure you're okay with that. We are multiplying or dividing by this. So think about how things cancel there. I brought the y up to get the negative 3. This is now in that form, except for now, I know I'm going to write it down here instead. N is negative 3. So here's the first formula that we're going to use. We're going to call this mu1, because we're going to have another mu later. We'll call it mu2. So mu1 equals y to the 1 minus n. Right? N being negative 3, we get 1, or y to the 1 minus negative 3. That tells me that it's y to the 4th. Yeah, make sure my notes are right next to me, make sure we're on the same track. We are doing well. Mu, sorry, that's how we say that letter. Mu1 is y to the 4th. Okay, so now we can actually take the derivative of this mu1 with respect to x. And when we do that, we get 4y to the 3rd. This is implicit differentiation. I don't know what y is. I just know it's in terms of x, because that's what the equation tells me up here, right? All the x's. So that's what I get when I take the derivative of both sides of that equation, right? The left side, I just get d mu1 over dx, and then I do the derivative of y to the 4th, but then I got dy over dx because I don't know what y is. This is implicit differentiation from Calc 1. Okay, now this is why this thing is not intuitive at all, is we are going to multiply by, let me highlight our formulas here. So this is a big one. We have that, and then I'm just going to highlight this because this tells me what to do next. But I'm not going to highlight the right side because it'll be different based on whatever that is. So there's a formula for that. I will write it here. It is going to be, so 1, what is that? 1 minus n times y to the, if I minus 1 for that, I got negative n. That's that formula. So this is what we're actually multiplying by. That's the derivative. And then times, this is dy over dx. So this is the formula for both those equations. One equation is mu1 equals y to the 1 minus n. D mu1 over dx is just the power rule. this mu1, 1 minus n comes down, and then I lower the exponent by 1. Well, 1 minus n minus 1 is negative n. And then I don't know what y is, so it's a dy dx. This is what we multiply, that expression right there. So I'll write that down. That is 4y to the third. That's what I'm going to multiply by. I knew that was it because we already wrote it down. We already figured that out. All right, so I'm multiplying the dE above by that 4y to the third times dy dx. That's the very first line up there. Multiplying this next thing, okay, so I get the 4's cancel. I get x over x squared plus 9 times y to the fourth equals, and then multiplying it by the other side, the y's cancel, and I get a nice 4x squared plus 9. The y to the third goes away. All right, why we did this is now this becomes the product rule. I lied. It's not a product rule yet. We are going to get to that. But what we're going to do now is we're going to replace everything to get it into terms of mu1 and x. So I'm going to replace, notice, let me get a different color to highlight here. This whole thing is equal to this, right? Check out the expression here. That's what that is, right? Those are the same ones, same expression. So I'm going to replace that expression there with d mu1 over dx. I replace that. I'm going to leave my x's. I'm okay with x's. Right? But y to the fourth, if you notice, this y to the fourth, let's do a different color here. Pink. This y to the fourth is right here. So I can replace y to the fourth with mu1. And then the right-hand side only has x's. This is now a first order linear dE. So remember, and I'm going to keep saying this throughout the semester, we talked about this at the first of the semester. When we work with solving equations, we always increase the method, make it more difficult. That way, when we manipulate it, we can get back to something that we already know how to solve. Like quadratics, we factor, and then they're linear equations usually we have to do after that. Same thing here. You make these right substitutions, then this dE down here where I started is now just first order linear. So now this is where the mu2 comes in. So let's do that. Mu2 is e to the, it's the integration factor, integrating factor. X squared, let me fix that 2 up a little bit, plus 9 dx. All right, this is just a u sub. I want you to think about, okay, we get 1/2, and then it's going to be 1 over u. So it's going to be ln of u. So we get ln of x squared plus 9. That's going to be positive, so we don't need the brackets. We can just use parentheses. Plus c. I want you to think about that integration for a moment. It's a u sub. I'll write the details here so you can stop the video and check it out. Do u equals x squared plus 9. Then du is 2x dx. So that's 1/2 du equals x dx. Follow through with that and you'll see how I got there. Okay, so we have that. The 2 for that can, or the 1/2 can be brought up. So we have e ln, let me go back to my green, sorry about that, equals e ln of x squared plus 9 to the 1/2 power plus c. This is C1. I'm going to call that C1. We get, just like we were used to doing back when we were doing these in our first order linear section, the x squared plus 9 to the 1/2 comes down, and then we just get this new constant here times c, because it's e to the c1, and we just call that c. So I have what mu2 is, but back when we were doing first order, we would just choose that to be a 1. That's what we were doing. It would just work out for us. Choose c equals 1. We can't do that every time, but in this case, the c's are just going to cancel out. Okay, so we have mu2 let's go ahead and just jump to the next page. Mu2 of x is equal to x squared plus 9 to the 1/2 power. So I'm going to multiply, just like first order linear, I'm going to multiply our dE by that. So let me rewrite my dE down here. All right, plus x over x squared plus 9 times mu1 equals 4 times x squared plus 9. Then that's it for that. Okay, so I'm multiplying both sides by that. So I get x squared plus 9. And we're going to go ahead and trust the theory for this on how that's going to work out. We can write it, I guess. D mu1 over dx plus, and then if I multiply by that, I get x over x squared plus 9. It's to the first power, so it cancels with half on the top. So I get that equals, and then that times that, when I have a 1, I get a 3/2. So I get x squared plus 9 to the 3/2. Multiplying everything by that. What's really nice is this turns out to be the product rule of our integrating factor times our mu1, our independent variable. And then the right side, I didn't change anything. All I did was change the left side, manipulate. I didn't even do anything else. Okay, I have that. I know it's that. So now I can take the integral both sides. So let's write that out. So much rewriting. Yay. Times mu1 dx equals the integral of 4 times x squared plus 9 to the 3/2 dx. All right. The left side's nice and easy. We just get the integrating factor times mu1. The right-hand side, though, we have an integral we have to take care of. Let's do a u sub. So u is going to be x squared plus 9. So du is 2x dx. So it covers most of that. So I'm going to have a 2 outside. And then I have u to the 3/2 du. Right? This is x squared plus 9 to the 1/2 times mu1 equals, okay, I raise it, so I get 2 times u to the 5 over 2, divide by my new one, which is 2 over 5. And I'm going to have a plus c here. I'm going to call it a c1 just in case I have to change it. Then I have x squared plus 9 over 1/2 times mu1. And then I replace my u. So u was x squared plus 9 to the 5/2. Oh, and we should multiply that front number by that 2/5. Oops. So that's 4/5 plus c1. Now, all it is back sub. This is just a first order linear differential equation. I'm going to back sub mu1, so I got to go all the way back up and find mu1. Mu1 was y to the 4th. So I replace that. X squared plus 9 to the 1/2 times y to the 4th equals 4/5 x squared plus 9 to the 5/2 plus c1. We didn't actually even change c. All right, I think we could do one more step to clean it up. I'm going to multiply everything by this thing here, but to the negative 1/2. Okay, so y to the 4th now is, okay, if I do minus 1/2, I get 4/5 x squared plus 9, and minus 1, I get 4 over 2, that's squared. And then I'm going to have a plus x squared. This is what I was just multiplying by. But I got to multiply it by it, so C1. And there is a great answer. You could throw C1 in front if you'd like. If it bothers you, it really doesn't matter. So there's my solution. If it was an IVP, I then now would plug in X and Y to find what C1 was, and then I would have my particular solution. So this is my general solution to this DE when the DE is a Bernoulli DE. Quite a bit of work, but if you get really good at the first order linear equations, you can switch your brain to that method halfway through, right? So you're not actually holding on to a whole lot of information. You just have to remember how to get it to a first order linear and then turn that memory on for your algorithm for first order linear. I would not let go of that. All the way through the semester, you will use first order linear all the way until the end.